and I have to import what you have done in the morning. I will import the geometry. This already. Cannot see very well, but maybe you can see. Do you have a similar discretization of your river and cross section? Yes? Yeah?
Yeah.
Okay. So what is very important here is the river flows. Here is the upstream part of the river, and it flows on that direction. And as you have seen yesterday and today in the morning, as you have talked, this cross-section is not straight. There is a floodplain area here because the flow path is actually on this side. And they are all regular cross-sections. Now that we have this geometry, we will create the upstream hydrograph. If you look into, we will now inspect the Excel file that I also shared it with you. So I will ask you to open the Excel file that in this Moonsheet data, there is one Excel file, inflow and structured data. I will ask you to actually open that file. There is inflow and structured data. Open that file.
Please open the Excel because you need to copy the data.
So, can you see? It's very big. I put it very big, the computer, hopefully that you can see better on the screen. So you have three tabs here. The first one is inflow hydrograph, then storage areas and lateral structures. We start with the inflow hydrograph. So the inflow hydrograph is for 64 hours. So you have 64 hours of data, and we have data every 1 hour. So every 1 hour there is the value of the inflow hydrograph. So we will input this data. The advantage in HEC-RAS is that you can copy paste from an Excel, or normally, because sometimes you might have a series of data for 10 years, that is not easy to copy from an Excel hydrograph. HEC has a system that it is called Data Storage System, DSS, and for very long time series of data, it's good that you use that DSS system. So everything is stored in a DSS that is not decision support system, it is data storage system. Well, there are many acronyms for the same acronym for different things. So this DSS you can even download if you wish from HEC website, a so-called DSS view. And you can see these data in the DSS view. And through the DSS view, you can create a new storage file. But this is how you can input data in case that you don't put it directly in the system, but you tell to the model, read in the DSS file. We don't have so much data, 64 records. It's okay, we will use these 64 records. Leave this Excel spreadsheet open so that we can copy paste from it And now we go to HEC-RAS to create the inflow file. In order to create an inflow file, you have these buttons here, which are not very visible here, but on your computer it might be more visible. Or in Edit, you have Unsteady Flow Data. So if I press Unsteady Flow Data, it comes with the environment where I can introduce this data. And
can you please magnify the window? Unable to read.
Well, I cannot, it's not because I cannot magnify more than this window. This is at the maximum resolution that I can project. It's because of my computer that you see it like that. But if you cannot, they are here to, well, I don't know, this is computer group who takes care of these screens, not us. So maybe you can show where that is more than this. I was trying to put it as big as possible so that you can read it on that screen.
Yeah.
Yeah? Can you see it? Some of the buttons you don't see it on the big part. So I have boundary conditions. You can see from the geometry file that there are two boundary conditions. One is the most upstream river station, and one is the most downstream. The 237 is the downstream river station. The 15,696 is the most upstream. The inflow comes on the upstream river station, so I will select the upstream.
And in the case in the steady flow, it's
We
just
are not in steady flow, we are in unsteady.
In the case of that one,
In case that you press the steady, you close that one, forget about it, and open another one for unsteady, yeah? So as soon as I'm selecting the boundary condition, it says select boundary condition location and then select the boundary condition type. There are only three boundary condition types available for that upstream. It's stage hydrograph, flow hydrograph, and stage flow hydrograph. What we have here available is a flow hydrograph. You might also have water level, that is a stage hydrograph. But we have discharges. So I will select stage hydrograph, flow hydrograph. I'm saying one and doing something else. You know how the mathematicians are. Usually they say A, they mean B, and then write on the board C. This is how it is. And you can see, let me take this. It's easier if I take this than with my phone. So, is as I said before, if you have a DSS available where you have a lot of data, you can read directly from the DSS. We don't have this. We have data at hand. So we will enter this table. You can either set up a date, a fixed time date, and let's set up a fixed time date today at 12 o'clock. We will put the date and time. It says here the data time interval, so it will be 1 hour. And then here we have the number of where we put the data that we have. If you scroll down, you will see that there are maximum 100 coordinates that you can put, and maybe you sometimes have more than that. Then you can change this by selecting here number of ordinates, and then you can put 150, 200, because the maximum by default is 100 here. So let's introduce that data.
In the new data.
So I will put as a fixed start time the date of today. I think it's 25th, yes? 26th, sorry, this is what I meant. 26th September. I thought when the course started, and this is why.
Unsteady.
And the time I will put 12 o'clock. And you see that automatically, because it is 1 hour time interval, and the date automatically is showing me the date. Yeah? Now I will ask you to go into the Excel spreadsheet. It is open, and select only the value of the cubic feet per second, not the time, because the time is already set. So select the whole column there. Control C. And now you go to HEC-RAS. You cannot really do Control V or paste immediately. You have to select the whole range of cells. Of course, that ideally is to select 64, but if you select more, it's okay. Only if you select less, it's not good. And then you just do Control V, and then if I go there, I can see the values of the discharge. Yeah?
Yeah, so now you are in the project, so now you can add your study.
You have it? Now down below to this menu, you have one option which says plot. Just select, because I connected the computer and I made it the maximum possible resolution. I don't have my chapter to disconnect it to but you can plot it. I will disconnect, access the plot and reconnect.
Have access and paste it.
And also put the
You find it. Only 26.
Plot the data and then I can connect the values. Yeah, so you should have something similar, yes? Do you have it? Okay. So what we have here is rising hydrograph that goes from around 13,700 cubic feet per second. It rises, then it is constant for a while, and then it goes down. Let's see if it will create flooding on the river, in the one river. And if yes, let's see if we can manage the water in a different way. Can we reroute it on the floodplain or on some areas? And this is what we are going to do.
Can you paste it? Yes. Right click.
So you can close
You
it,
should select many times. Select.
close,
Select yes.
say OK here on the data. And now the flow hydrograph is there saved. The next thing that we are going to do is to put the boundary condition downstream. I hope that I'm here. Now down here, the flow, if you select the second, sorry?
When you slow down a bit, they have to touch up.
Okay.
Plot.
Can I help anyone?
Data plot. Basket.
Yes. Error plotting. It says subscript out of range. Are you sure that you copied it properly?
How you plotted this? You select from the Excel. And select, you just select this one. Okay. Copy. Because the time is here.
Here it is.
Now
Yeah? No, I don't really know what
you
was wrong.
can Ctrl paste, Ctrl V. Yes.
Yes?
Just paste all the number.
No right click.
Yes. Okay. Date okay. Now I think data plot. Yes.
When entering the date, guys, remember that the time should be in using column. So 2 point, the column, and 0, 0. If you put a point, it's gonna give you the wrong. So it should be always the column, okay?
Okay. So now we put the next condition. Can I go to the next, to the downstream? So as you have seen yesterday, we cannot do anything unless we put the upstream boundary condition and the downstream boundary condition, because the numerical scheme requires both boundaries to be defined. And then if we select the most downstream, we will put normal depth. We can also put hydrograph and as a friction slope, let's just put 0.004. So what I put as a condition is normal depth so very mild slope, yeah? Rest okay. And then you have a second tab where it's written initial condition. You see? Select that initial condition. And initial flow means how much flow is at time t equals 0 when we start our computation. How can you see that? How can you know that? You just look at the inflow hydrograph and the upstream boundary condition, and then you read from there, yeah? So it's 13,700. I think this was 13,500. I want to tell you something else. Even if I put 700, I can tell you that the first hour, the errors might be small there, but after 1 hour, everything will be wiped away. So the numerical scheme has this advantage that any small error, I'm talking about small error that you introduce, it will be wiped out in the first steps of computation. So you don't have to worry so much if it is 13,500 or 13,700. It will be wiped away. If it is 500 instead of 13,500, it will still be wiped away, but in a very long time. So small errors are wiped away. What you have to remember is that not to rely on the first computational steps, so that you start looking at the results only after 1 or 2 hours. So if you run for 64 hours, the results are very good after 2 hours. Of course, if we put now correctly 13,500, then it will be correct. But in your daily practice, you should not be so precise in the initial condition to the after the digit, so that you have a number and you put 13,500.74. It doesn't matter. That small error will be wiped away. Yeah? Unfortunately, we don't have the time mathematically that I prove it to you. You have to believe me. But, it is proven mathematically. It's based on the so-called method of characteristics. Okay? So if you want to look yourself. Now that we have done this, we do file, save unsteady flow data as, and I will save it, I will give it the same name, Muncie 1B. Press OK. And now we can close this. If it is saved, I will just close. And then automatically you will see that you have the description, the project, the geometry, the unsteady flow. Of course, because it's unsteady, we don't have steady flow. All that we need to do is really to run the model, and then we will have a plan here. This is how the result is called, a plan. Now let's go to the running. You cannot see here from what is projected, there is a small man running uphill, but you also can do in run unsteady flow analysis. Yeah, you select unsteady flow analysis. And now we have the geometry file. This is a very important. You see that in case of unsteady flow, the computational setup is a bit more complex than in steady flow, which is to be expected. You will have programs to run the preprocessor, and we will check all of them. Then you have starting date and ending date of the computation. And we have to say the computational interval, yeah, for this. We can compute every minute. We will not save every minute because this would be too often to save every minute. And we want to look at the interval. Let's say that normally if we have data for every 1 hour, we will look at every 1 hour. But let's say that we look every half an hour what is happening in computation. And like before, we will save the plan. Before we do that, we have to mention that we want results at each cross-section. So you go into options, and then you have as a first option stage and flow output locations. Do you see it? Select that one. And then you see all the cross-sections that we have. If we don't select them, then HEC-RAS will compute all these cross-sections, but it will only save data and results in the result file for the first and last cross-section. We want to look at each cross-section. So then select, there is this small arrow, and say all of them. And now that they are selected, you can close this one. Again, I don't have access to, because I just press OK. Now let's save this plan. We will save file, save plan as, and I will call it plan 01 because that is the first plan that we are doing. And I can also add a description, 1D liver flow. Okay. And then here I will just say plan 01. Hopefully that you will remember for each plan what do you have. And then say OK. And now we have to do what I have said. Geometry preprocessor, unsteady flow simulation, post-processing. We don't do mapping on this 1D. You can check it, but it has no effect. Yeah? There is no mapping. Starting date. So it was today. Okay, 12 o'clock.
And then a short identifier, you can just put blank
column
01.
00. And the ending date, well, after 64 hours.
And then she selects this tree.
That would be
So you're going to pre-process the geometry, do the simulation and the post-processing.
okay.
And now she's
Not up
entering
to the end
the
of the
start
date.
date.
6 hours missing.
First three.
The first three, we are not doing any
So we're
mapping.
28 here.
It's 20. It's today, 26th of September. We're at 12 o'clock.
And if we put 12 o'clock,
But these are here in the starting time.
let's put 12 minus 8, 4. Let's put 2 o'clock. Is it clear what I have done? We have 64 hours of data. So if we start the computation from 26 September, 12 o'clock, with 64 hours of data, it's almost 3 days. And then, it's less, 12.
You can always measure when you know data.
September 28th.
September 28th, yes. And I said, okay, ending date 2 o'clock, because if I put 48 plus 20, it will be 68 plus 4, 72. So I didn't put up to 12 because there are 8 hours missing out of these 64. Hopefully I don't have to put 1 o'clock. We will see now when we start the computation. Press save once again. Save plan. And let's put here 10 minutes because otherwise it will compute too often every 1 minute. And if you remember, we said that we will look at the results every 30 minutes. 30 minutes. And now press compute. Oh, for me there is something wrong here. Do you have the same error? No. I will come and see that yours is running. I know what the problem is.
Check it.
Do you have 30 hours? Yes, 30 hours? 30 hours. No, 30 minutes. Not 30 hours. Yes, 30 minutes. 30 hours. So long. So long. 30 minutes. Ah, you're missing something.
Input time should be 1 hour.
You did save? File plan. File plan. Just save. Just close. Close this one. I just close. Cancel. Okay. Cancel. Yes. Can you back? Yes, close. Can we back to the first screen? First window? Briefly. Okay. Here. Let me see. 2 o'clock. Yes. 30 minutes. Everything is okay. See. Should be okay. Yes. We save everything. Plan done. Okay. Date. Your date is 26, and he is 28. You can't do this the same date. Okay, now it is 28th of September. Okay, that's good. Let us try. It's not so.
Good computation, because I need to ensure that this condition mathematically is met. This is part of numerical analysis, of the numerical scheme that we are using. Well, let's have a break and then look at the results after the break. If there are other questions, first we answer the question. Does this answer your question? Next, we look at the results. Yeah, so we did the computation, and now we look at the results. So in order to see results, there are some buttons here. here in the end of it, where we can see longitudinal profile, X, Y, Z, and 3D, or here in view. We can have exactly the same access to the same buttons. The second button, well, it's not the most coherent so you can see the main channel and you see the water levels. Do you notice anything?
Which option is this?
Well, I will show you once again. I will close. It's after this is a RAS mapper, then there is cross section, and then the next one is profile. You see it? View profile. This is the one.
Yeah, beautiful.
Well, I don't know if you have the same view as me.
They are different.
You have different view.
Yes.
Interesting.
Okay.
Well, you have different, let me see. Well, the ones who are having the same as me, yes. So you have the line,
Yeah.
it's okay. Yeah, that is okay. What is this?
Green one.
The green one. One is the energy line and the other one
Yes.
is, yeah, so if you look, there is the energy line, there is, so there is, somehow, well, your results are good. My computer, I don't know what, your results are good. Yes, this is how it should look like. Maybe it's just the screen, because your results are good. What did you do? Yeah, all of them this is, but we didn't do so many profiles. We only did one profile, so I don't know why it's like that. So then you see the whole time steps. This is why this is, if I say only plot initial conditions, if I just put the initial conditions, then you will see the discharge that I initially put, the initial profile, and the energy line. So that is how the water is there. And then you also can do an animation that is better in the profile. If you select this one, animate the simulation results, there is here animation control, and then, well, it's very fast. That is because it's every 30 minutes. This is why it is very fast. Can you see in your case? No, you cannot animate. Well, this is also computer dependent. But can you see on my screen? Well, this is an extremely good software, but sometimes you have to close it and to reopen it. So very seldom, but sometimes this is happening in order to see animation. Can you see? Can you close?
This?
Yes.
Fine.
No. No. Can I try?
Sure.
Okay. Yeah, well, you only have one profile there. This is why it doesn't. You only have the initial conditions. Yeah, so did you put all those before when I said compute? I said to include this stage and output hydrograph. Yes, you put it all. And post-processing, everything here, 10 minutes, 30 minutes. And everything was okay, yes? Because somehow I close, and then if I do the view, now you will have it. Yeah? Does it work for you?
I close it.
You
Open
close it
this.
and reopen it, yes. Let me see. Does it work? It's working, yes? Okay, good.
Yeah.
Does it work for you?
And also I can adjust the time.
Yes, animation speed. Wow, I don't have that. Though I have 503. Because that is, you have an older version of HEC-RAS or the 503? Because they have the animation speed that we don't have. We don't have, they don't have. They have an animation speed. Oh, okay. But it works for you, yes?
This is critical, I guess.
Okay, something.
There may be some intervention for structure.
So this will
Works? Okay.
But is there any structure there?
No, there is no structure, but let me say to everyone, let me just project it. You know that the water level is actually, it should project in a, no. The projector is, I don't know why it doesn't want to.
Sleeping. Powerful.
when you put all of them together by sitting.
It doesn't want to project, let me take it out and then I will talk.
Power is off, I think. Yeah.
The power is off?
Yeah.
We had the same problem yesterday, yes?
Yes.
Uh,
Yes.
So maybe it is scheduled at a certain hour to switch off.
Sleep mode.
Well, the question was why the water level is not smooth and in a line. Well, if you look to the river is meandering and it's quite long. It is, did you compute how long the river was?
15.8 kilometers.
Okay. And here you see actually the riverbed from one section to another, but you see it in a straight line, though it is going as if you would put a string and you take the string and you show it as a one line in this screen. There is a lot of distortion in this screen because here the elevation are very big. You see the on Y and here on X there is a lot of length. So this is not at a real length. So that the ratio between the vertical and the horizontal is fully disturbed. And then because of that, you might see here as if there is something there. There is nothing. The water is really straight and the slope is very smooth. It's just because of these differences between horizontal and vertical, the ratio, the representation between horizontal and vertical. If you would put the elevations at the same scale as the horizontals, you will not see anything here. It will be so small that you will not see anything. Yeah? So that's the reason why you see it like that. It is clear. If there is a structure there, then you will see a special sign in the vertical. We will see in a moment that we will do structures. The moment that you introduce a structure perpendicular to the flow, in this view, you will really see a line that will represent the structure, or even laterally. You will also see the lateral structure. It's just a viewer. Let's look to other type of results here. Now I will close this one. And now, apart from this profile view, you also have XYZ or view. I will select here. You see here XYZ perspective plots. If I select XYZ, Now you can turn a bit this XYZ. You have here on top how to turn it. It's not the ideal. Let me rotate it. No, this is how it is. So now in this XYZ you see the whole river length as it is in reality. You see how we put the cross sections and how wide the cross sections are. And you see the water level that has been computed. The advantage is that you would see when the water level goes out of bank. Out of bank means that it goes beyond these red points in the cross section. Out of bank would mean that it will create flooding. Yeah? So can you identify a region here where the water goes out of bank? It goes here.
Yes.
Yeah. It goes a bit here out of bank. It goes here. It goes here. Almost everywhere, the water goes beyond the banks of the river. It goes to the river banks. Let's look in another way at these results. I will close this one. And then we have not these, but in the cross section. So here is a cross section view. In this particular cross section, which is 15,696 in the upstream, the river banks are defined by these bank stations. Everything, the moment that the water level goes above, this is at the end of the simulation, it is flooded. Yeah? And now you can go through the cross sections. We can also animate here to see how this evolves in time. And you can go through different cross sections and see what is happening. Now let me talk with you on this cross section because this is important. It shows something that I want to show you. You see, our cross section in the model was defined up till here. It contains the floodplains, but it is the cross section of a 1D model. You see what is happening here? There is a vertical wall. So as soon as the software doesn't have a cross section where to compute, it adds two vertical walls and it will compute. Well, this doesn't go, it will not add, if the cross section is, let's say, 10 meters, it will not add a vertical wall of 100 meters. It will tell you something is wrong in the definition or in the amount of water that it is coming, because 10 times more than the depth of the cross section would be too much. So normally a software allows to 4 times the depth of the cross section to go as a vertical wall. As soon as you see in a section a vertical wall, it means that there is flooding. In the past, the 1D models, if they were not containing the floodplain, if they were limited to the cross section and the vertical wall was computed, then what was mapped was the limit of the upper part of the vertical wall. It was overestimating the flood, but it was always from the point of view of protection and people of imputing the damages was overestimating, but from the point of view of protection and building a levee, it was better, more costly, that's true, but it was safe to consider more water. Nowadays, that the 2D models allows that we compute more clearly the 2D extent, then with such model, you only detect where the water will go out of the cross-section, and then you will do the 2D modeling to determine the proper extent of the flood. Yeah?
Here it depends on the extent of the cross-section we draw in the file, or?
Well, it also depends on the amount of water that comes from the
No,
upstream.
if water is also crossing the extent of the cross-section
Well,
line.
there is no data beyond this. So the software is a software. It computes an area of a cross section. If there is no data here, it has to have a solution to be able to compute. So it extends as a vertical wall. But of course, it also checks how much it has to expand. Yeah? Another way to look at this result. Let me show you another way. So there is also the time varying this one, plot stage and flow hydrographs. You see one before the last part. And here you have stage in which cross section? Here it's 14,856. Let me select the last cross section. There where we inputted the flow is this one. And let me, because they are both stage and flow, let me just switch off the stage. Let me just let the flow. So you can see here that you have the maximum value. Is this the hydrograph that we inputted? No. I hope yes.
Yes.
Not the one we did.
This is the one, yes?
Yeah.
This is the hydrograph that we input for those 3 days. This is for the most upstream station. Remember what is this value, yes? It is slightly above the 20,000. Let's look to the last station. Well, here it means that you know the numbers. So what is the value here? It's also close
Above 2,000.
to that. It's more smooth. So let me ask you something. Is there attenuation here? Not really. So there is a lot of water coming there. Yes? There is not a lot of attenuation there. Yeah?
But in here it's around 928 for the same station in my case.
Well, I will look at your station. You can look here at the time series. The maximum is 20,000 here.
Oh, yes.
999 here. Yes? And if I go to the last station, there,
Yes.
it's 21,000. So the difference is not noticeable. Yes? So that means that there is quite some steepness there because what enters goes out. Yes? Well, let's run the same model with another normal depth. Yeah? And let's compare and let's see. We will name it as plan number 2, and we will run the same model with a slightly different. So let me show you how you do that. We open the unsteady flow data. We go. Did you open the unsteady flow data?
Yes.
Yeah?
Yes.
Let's go to this normal depth. You selected it?
Yeah.
Then we open this normal depth, and instead of 0.004, we put 3 zeros, 1, 2, 3, and then we put 64.
3 zeros?
3 zeros, and then 64. Three zeros, and then 64. Press OK. And then say save. don't say save as, you just say save. Now we go to the running. And here I will save this under another plan because I don't want to override the previous values. I want to have an extra, and I will say save plan as plan 02. That's okay. And I will call here plan 02. That's okay. I will be sure that I save. And then I will press compute. And it worked, at least for me. Did it work for you?
Yes.
Now I will close it, this one, and I will look at the results again. Let's look at discharges. Which one? Did you save the unsteady part?
Yeah.
And then if you go to this running, unsteady flow analysis, you did? Yeah? But it has to be plan 2. So before you do anything, you say save plan as, save file, save plan as. Save plan 2, okay, press OK. Plan 2, right, plan 2. One more one, you see? Okay. Put it now. Now we close. Yes. Normal, that's the downstream. Only shows you normal water step out. The outlet. Do you have some changes? Let me see. So I will close this and I will look to the discharges. This is the most upstream part, which should be the same because it's the input. And this is the most downstream part. Is there a difference? Yes? No.
No.
Well, let me explain what is this normal depth. Please use. So this is the downstream and this is the upstream. Yeah? And the river flows in this direction. Here we have a hydrograph. And here we have normal depths. That means that at this particular point, we define the slope of the river downstream of this point, and it was 0.004 or 0.00684. What does this mean? That means that the water level here follows a normal depth approach, and the amount of water or the water level that it is maintained here is the normal depth for such a slope. Yeah? This is the amount of water that goes out. Well, the difference between these two slopes for this particular lever, only at the end of it, it's quite small.
It means in first condition it is taking more water than the second condition.
Yes, but still it's very little water taken out as compared with how much water it is coming.
Slope.
Yeah?
Slope. That is a slope, madam. Slope 1 in 1564, that is a 0064.
Well, this is the normal depth here.
Normal depth, not slope.
It's normal depth. It's not
That is
money.
because the slope is there to normal depth.
Normal depth means
It's a normal depth here, the water level here, and it determines how much water goes out of the system. But there is so much water as compared with how much it goes out of the system that it cannot take too much out. This is why this discharge is not changing so much. Yeah? So my advice to you is when you do unsteady analysis, unless you are sure that the water level is constant there in the downstream, that you try to put variation in time. Here it is normal depth in the downstream. So we have a flooding here. How are the managers of this river managing this flooding? They decide to put the water outside on the floodplain near the river. So not whenever water comes, to let the water flow into the area that it is near the river. And we will model to see what if we have storage areas here. That means it's as if we have a bucket in which we put the water. This is storage areas. And then as a next step is that we will, instead of having storage areas, we will have a 2D area that we will model in 2D to see what is the flooding over that 2D area. So what would be the difference between the two? When you have storage areas, that means you take water out of the river through a lateral structure or through some and then you might have several storage areas here. Maybe here it's an agricultural area and you have small dikes, and then these storage areas are communicating between themselves through small weirs. Yeah? So how do we take out water from the river and we deal with storage areas? When we deal with storage areas, we are only interested what will be the volume as H is changing, the volume of these storage areas. We are not interested in how detailed the digital elevation model is in that area, but how much water the storage area can keep. Yeah? So this is what we will do next. We will model the same river with storage areas. At the end, we will bring the results at cross-section, at the end cross-section, as the river is, the river with the storage areas to see if less water arrives here. And then when we have the flooding, we will compare the water in the storage areas and with the water when we have 2D model. Okay? Can we stop with 1D and go for the 1D plus storage areas? Or you have questions still about the 1D part? Of course, you can select any other cross-section to look at the results, but I think that's clear, not only the last one, I think any other cross-section. Yes? Okay, look at the stage. And okay. Okay, then I will close this and I will do a new setting where we will put the storage area. So I will say file save project and then I will close this one and do a new project. New project. So now we go on a new project.